Okay, so um, there's just two problems here working with these rational functions. One, you're given the function and had to find the information. The other problem, you're sort of given the information in terms of a graph, and you had to come up with a function, right? So it's trying to connect those ideas together. What we see on the graph, what we see in the algebraic function, and what we see in the algebra to the graph, back and forth. So a couple comments here. Um, First of all, you've got to make sure that you got to make sure that you factor when you're working with these rational functions. I've got to see what's going on with the function before I can begin. And so, the top here factors is x plus 2 and x minus 2. This is better, x plus 2x minus 2, right? And the bottom is this 2x plus 1 and x minus 2. So this here, what that does is this is not a vertical asymptote in the bottom. Because it's a common factor between the top and the bottom, it actually creates a hole in the graph. Okay? And so what we do is we just work with the rest of the graph, ignoring this part that I've X'd out in red. And at the very end, I'm going to put the hole in and show it on the graph. Right? So that's how we want to deal with this situation. The vertical asymptotes come from where the bottom is 0. And again, a lot of people did this correct. And you get minus 1/2. The horizontal asymptote, we look at the ratio of these terms there, which is 1/2. The x-intercepts are from the numerator, which is going to be minus 2. So 2 is not an x-intercept because 2 is taken off the board really because of this hole. And now we can put all of that together into our graph. I have a horizontal asymptote there at 1/2. I have a vertical asymptote at minus 1/2. I have an x-intercept at minus 2, which is right there. Should probably have moved my graph down. Kind of committed at this point. And there's no other x-intercepts over here. So what that tells us, there's a couple ways to figure it out, but that tells us the graph kind of comes down as I go towards the asymptote from the right and comes down here as well. And this is where the hole comes into play. It's a little bit big and clumsy. See if I can do that a little bit better. You can also just indicate with a little arrow and a little dot. I'm okay with different ways, but you've got to show that that hole is on the graph, and that hole comes from these common factors. Are there any questions about that first problem? And obviously, I know, you can graph some of these independently, look at a graphing calculator or something, but that's not what we're trying to do here. And I can certainly write problems that make that not possible to do, or not possible to do without me seeing it, right? So make sure you're able to do that work independently. Any questions? Okay. Let's look at the next problem here. And this one, I thought the way you guys approached it was interesting. So there's two, what I saw in the take-home work is there's two good ways to approach it. I was approaching it, or imagining that you would approach it one way. And the way I would have approached it is I would have said, okay, here is the horizontal asymptote, right? And that's at 2. Here's the vertical asymptote that looks like 5. And here is the y-intercept, or the x-intercept, which looks like about 4.5. So what I would do then is I would write my function by making sure that the x-intercept goes on the top. So x minus 4.5. And the vertical asymptote goes on the bottom, x minus 5. And then, so that part there gives me the right information for the horizontal the vertical asymptote and the x-intercept, but it doesn't give me the right horizontal asymptote. This would have a horizontal asymptote of 1, but I want a horizontal asymptote of 2. So if I put a 2 in the numerator, that's all going to make that fit together and give me the right function that I'm looking for. So that's how I was sort of expecting or thinking people might approach the problem. But a number of people noticed that, hey, this graph actually looks a lot like this graph, which is our 1 over x function. And so they attacked this by using transformations instead of the strategy I used. And they said, well, it's been moved over to the right 5 units, and it's been moved up 2 units. So given that thinking, they would have written the function like this: f of x equals 1 over, if I want to move it to the right 5 units, that's going to be x minus 5 instead of x. And then if I want to move it up 2 units, that would be a plus 2. And it may look like these are different functions, but actually if you do the algebra, if you add these fractions together, x minus 5, x minus 5, you end up with 2x minus 10 plus 1, you get 2x minus 9 on top of x minus 5. And if you look at the blue version, you see, oh, that's exactly the same function. Okay, so those were two pretty different approaches, but they still led us to the same point. Now this bottom approach in red only worked because the function I was working with did happen to look like 1 over x. If your function, on the other hand, had some other, you know, if it did this and this and this, then all of a sudden we don't know what that base function is anymore, and we would have to probably do the vertical asymptote and horizontal asymptote strategy for that one. I actually really like that problem. I like that people approached it in different ways, but they're both great solutions. Any questions on that version or that problem?
Is that a minus or multiply sign with 4 and 5 in the blue?
Oh, that's a 4.5
5.
right there. Yeah, that's with my finger, because 4.5, because that's where I put the x-intercept right there.
Okay.
Right, so whatever the x-intercepts are, those have to be x minus that number in the numerator. Right, every x-intercept is going to generate at least one of those.
Okay.
Other questions? Okay. Okay. Any questions from homework problems at all? Anything?
Yeah, I did have a question, but I honestly forgot which one it was. I'm trying to sign in right now
Yeah,
to.
yeah, no, that's fine. Take your time. Um, you know, the big issues, of course, and I think we talked about this last week too, right, with rational functions, is just being able to identify these different features of the functions. So horizontal asymptotes, vertical asymptotes, x-intercepts, and holes in the graph. Those are our main things. We also have slant asymptotes, so I am going to talk briefly about those. I mentioned those last week, but we didn't actually find any. So I always think there's kind of two parts. There's being able to find all of those things, which is relatively direct. Find this, find that. But then there's also this part of kind of putting them all together to come up with your graph, and that can be tricky sometimes, depending on how many of those features you have. But it's we want to make sure we understand roughly what the graphs look like with these rational functions. They have a lot of similarities to them, and then it's just kind of choosing between kind of one or two options usually, and trying to figure out how to choose between those.
All right. So it's the section 4.1, question number 8.
4.1, number 8. Great. Yes. Okay. Okay, so what we have here is we have this function. So this is an application. So P equals 0.5 plus 0.9 times n minus 1 all over 1 plus 0.9 times n minus 1, where n is bigger than 0. And it says psychologists have developed mathematical models. I mean, it's not just psychologists, right? Everybody develops mathematical models to model or show what they expect to happen in certain situations. And that goes from like your small business owner that's trying to predict how many employees to hire, to the Federal Reserve Board of the United States of America that's trying to predict how many jobs are going to be gained or lost each month, right? They have models for these. So this is really where our math that we've been working on kind of hits the real world. And we don't see a whole lot of examples. Some of them are maybe not that compelling sometimes to us, but it really makes it important to dig into these a little bit, because otherwise, like, who cares about the rational function, right? It's just an abstract curve that doesn't really mean anything. But when you all of a sudden say, oh, well, that curve might represent something that I care about, then there's a little bit more need to understand the curve, right? So this is the memory performance. And whenever I do an application, I have to really think about what the variables stand for, because they're no longer just X and Y, they actually mean things now. N is the number of trials. So N equals the number of trials, and P equals the fraction of correct responses. So, what that's saying is that if you do the trial once, you expect a certain number of correct responses. If you do the trial twice, then we expect a different number of correct responses, right? So it's a function of the number of times we do the trial. And so in A, you're just completing this table. So n equals 1, and you plug 1 in here, and you should get a value for P. Well, n equals 1 is actually pretty easy because that's 0 here, 0 here. And I get 0.5 over 1, which is 1/2. So whatever this memory thing is, you expect to get the fraction of correct responses. We expect to get around 1/2 after your first trial. Maybe it's not super hard, right? You do okay. And then n equals 2, you do the same thing, but now all of a sudden you have 0.9 and 0.9, so you end up with what, 1.4 over 1.9. I don't know what that is exactly, but it's certainly better than 1/2. It's closer to like 0.6. So what that says is after 2 trials, my improvement has, or my memory has improved, right? I've learned a little bit, or filed some away. And we go through that. So well, in B, I mean, okay, or the second half here, P approaches what as N increases? And you'll be able to see that from the chart, but we can also see it because of what we know about rational functions, right? This is a rational function. And so it may look a little different, but if you multiply it out, you're going to get 0.9n minus 0.9 plus 0.5, which is minus 0.4. And here you're going to get 0.9 minus 0.9 plus 1. So that's 0.9n plus 0.1. So that's the same thing. So now we can very clearly see what's happening as n gets larger and larger and larger, as we get more and more and more trials. We can see this function has a horizontal asymptote of 1 because those leading coefficients are the same. So again, not quite knowing what happens in between here, we expect the values to get closer and closer and closer to 1. And remember, P is the fraction of correct responses. So if your fraction is getting closer and closer to 1, that means you're getting closer and closer to 100%, right? The correct responses over the total responses. So, you know, it's not, well, like earth-shattering right here, but it is an example of how analyzing the function can tell us things about the situation. And we can understand what the function is doing if we understand how rational functions work. If we saw some more complicated functions, we would also know how those functions work. So I got into some other things there, right, as I tend to do with these questions. But did that help with that question?
Yes, thank you so much.
Yeah, of course. I mean, I think the reality here is this is probably a question where it was maybe not totally clear what they're trying to get you to do, right? The actual doing it is maybe not that hard, but it's hard to know what you're being asked to do, I think.
That's where I got like, a little bit like, didn't know what to do. So
Yeah, I think it feels a little overwhelming sometimes, right? When you see an
definitely.
application like this, right? It's like, okay, what memory and P and N, and it's like, I don't know what any of those things are.
Yeah.
And that's really common. And I think that's why a lot of students, don't love the application problems because they feel harder. Our goal here is is to say, I don't really care what the application is. If I can see or get to that formula or that function, then I know what it is, right? I know the mathematics behind it. And so that's, a little bit in a nutshell of like why you're all taking this math class is typically there aren't that many mathematicians in these math classes. Maybe some of you will go on and be inspired at some point, but you're probably taking it because you have some other interest, right? Whether that's business or psychology or physics or who knows what. There's lots of different things. Exercise science. There's all kinds of different things. All those fields have sort of nothing in common except the math, right? Because all those fields have things they want to understand and model. And so we teach you this sort of X and Y math, which is very abstract. But the hope is that you're able, whatever field you go into, to use that those strategies when you approach that. So it is really good to ask questions about these, and it's also good to improve on our kind of problem solving with these. And I think part of that is just really taking time to understand the variables and kind of think about what it's telling you or what it's trying to tell you before kind of digging into the problem, right? So just like I did, I took some time to kind of write down the formula and kind of wrote down what the variables are, partly for me just to organize my thinking. And then I sort of thought about, okay, what does this mean when I start plugging in numbers? Like, what is that telling me? Because without that understanding, I'm likely to get lost later on in the problem. So that's one way to help with those application problems. Again, I know it was a straightforward question, but it brought up some what I think of are important things and some bigger picture things about math. Hopefully that didn't scare anyone else off of asking any questions. Are there any other problems you'd like to see or talk about?
I got a question about 4.2, number 18.
Let's take a look. Yes, okay. Any particular part or just the general?
The part where it asks us to find the x-intercepts and the y-intercept, like I get that you're supposed to use like the 12 and the 4 up there on top, right? To get to like factor that.
Yeah, whatever. So you may have different numbers here, probably.
Yeah.
But yes. So this question, for those of you who have it, who don't have it up or whatever, it says, find the domain, find the intercepts, find the vertical and horizontal asymptotes. Remember, those have to be x equal and y equal, right, for horizontal and vertical asymptotes. And then finally, plot some solution points to sketch the graph. So it's kind of like everything, right? Like, tell me everything you can find out about this thing, and then try and figure out which of these the graph looks like, right? So I would always start by factoring. It's possible sometimes you'll get pieces that won't factor, like if this were x squared plus 25, that wouldn't factor, and that's fine. It'd still be a rational function, but it wouldn't have some of the same features that this one will. So however it is, you want to factor it. Okay, so I think you said 12 and 4 was yours, maybe, so that's probably 6 and 2. So, minus 6 plus 2 or something like that to get that to work. Now that it's factored, I can start to answer these questions. Okay, so the domain, I can't have 5 or minus 5, right? Because those are going to make the bottom 0. And that's true whether it's a whole or a vertical asymptote. I can't put in the 5 or the minus 5. Okay, so if there's a factor of x minus 5 up here, that wouldn't change the fact that minus 5 or that 5 was not in the domain. And then the x-intercept, and this is something you got to file away if you have trouble remembering it. It's a good one to write down. The x-intercepts come from the numerator. So after it's factored and you've eliminated any holes, the x-intercepts come from the numerator. So x minus 6 equals 0, and x plus 3 equals 0. Okay, so those are my x-intercepts. The y-intercept, on the other hand, is just g of 0. So that's actually easiest to find back here. You can find it here too. I just put in 0 for x, but because the way a polynomial works, it's really easiest there because everything else drops out. I'm going to get 18/25. And I think, sometimes it's challenging because it feels, maybe to you it feels different, like, oh, what, we're doing kind of really different things to the x-intercept and the y-intercept, but really we're taking a shortcut here for the x-intercepts. The x-intercepts, you do set the function equal to 0. You set all of this equal to 0 is what you actually do, but the only way that's 0 is if the top equals 0. The bottom can't make a fraction 0. It's only the top. So that's why we end up setting these factors and solving them. And then for the y-intercept, we set x equal to 0. So it is the same symmetry that we do normally, but maybe it's taking a little shortcut to just say, look at the numerators directly. Okay. Then we look at the vertical asymptotes. So notice here, both of these are going to be vertical asymptotes. So it's going to be x equals minus 5 and x equals 5. And then the horizontal asymptote is also easier from this kind of original form. They're both x squareds. So the horizontal asymptote is going to be y equals 1, right? 1x squared over 1x squared. Okay, and then we look at the graphs and try and figure out which of the graphs it is. I'll show you these. It's a good question to talk through. Okay, so I've got these 4 graphs to choose from. They all have the right vertical asymptotes, so that doesn't help me. The horizontal asymptote, though, should be y equals 1. So that helps me a lot, right? Because there's only one of these that has a horizontal asymptote of y equals 1. It's this bottom one here, bottom right. I would also like to verify, the x-intercepts and the y-intercept, but those look good too, right? There's the x-intercept of 6 and minus 3, and the y-intercept was like just a little bit less than 1, which looks reasonably good right there. So I feel very confident that this version is the graph. Does that help at least with the thinking on that one?
Yeah, that really does help a lot.
Okay. Typically it's like you guys know a lot of the parts. Even when you're struggling with these, you actually probably know a lot of the parts. There's just like 1 or 2 things that you're not seeing or thinking of properly that's could be holding you back, right? So that's the goal here is when you struggle with it a little bit, then like, okay, I got all that part, that's fine. Oh, that part, I didn't really know where that part came from. Now I get it. Now you can move forward, right? And that's that's why you have to do the problems and kind of put in some of the work first, because otherwise, otherwise you don't know what you don't know, right? You can't. It's hard to see that without having put in the work. It's just like a whole flood of information otherwise. Okay, anything else? I know there was a question about the slant asymptotes, so let me go ahead and do an example of that.
I do have another question, if
Yeah.
that's okay.
Go ahead, it's a good time.
4.1, number 7, part B.
Yes, another application question here, right? Okay,
Yeah.
so we have these recycling bins, and the cost C is related to the percent of the population, 25,000 P over 100 minus P. So the cost of supplying recycling bins to, oh, okay, I get the cost of supplying it to this certain percent of the population is given by this function. So, and P is between 0 and 100. So, and when you have an application, you know, it's usually you can't just put anything in. It only makes sense for certain values. This formula makes sense for lots of different p-values, but in terms of the recycling bin and cost, it only makes sense here. And then I just want to make sure, like, I wasn't, I mean, I've seen this one before, but I was like, okay, does this make sense with my thinking? And so what I did was I thought to myself, well, what if I give 0% of the population recycling bins? Well, if P equals 0, then I get 0 over 100, which is 0, which is right? Like it shouldn't cost me any money to give nobody recycling bins. So that's another way of making sure we understand kind of what the function is doing, and is it really doing what I think it's doing, right? So if I give 50%, so I put P equals 50 in here, then that's going to give me a different number, a cost for the recycling bins, okay? And so that's really actually what they're asking here in B. They want you to, what if you give 25%, 50%, oh sorry, 60%, or 95%? And again, your numbers here may vary. What's the cost? So you have to be a little bit careful here, because if you're giving 25%, P then is actually 25, given the way this model is written and P is defined. It's not 0.25, which is actually equal to 25%. We're representing that with 25 when we change that into P. So the cost then would be 25,000 times 25 all over 100 minus 25. So that's what, 75. That's 3, right? 25 divided by 75 is 3. 25,000 divided by 3, what is that? $8,333, 33 cents. Rounded to the nearest dollar, so $8,333.
So it's not going to be 0.25 because it's a percent?
Well, so if we look at what it says, the way it's written is that it's P percent. So the P value that's going in here is actually then the 25, not 0.25. Because of that's just how they made the model and how they defined P. So, right, like if it says in the definition, we're supplying recycling bins to P% of the population. So if you're giving it to 25%, then the p-value is actually 25.
Okay.
The percent. Again, I mean, it's just, that's how we define the p. I mean, you can define the p however you want to, but we got to be consistent with that if we want to make the model work for us. We know 25% is normally 0.25, but it's not asking for what 25% is equal to. It's asking for the value of p to put into the function. I don't have a better explanation, unfortunately.
That helps. No, thank you.
That's at least the way it is. I don't love how it's defined either, I think, but that's how they have it set up here. Okay. Okay, so yes, there's the question about this horizontal asymptotes. That's actually a question about oblique asymptotes. So that's a perfect lead in here. That was a question in the chat. It's a perfect lead in here to oblique asymptotes. So we remember if you've got like x plus 2 over x squared minus 9, this is going to give us a horizontal asymptote of y equals 0. The bottom degree is larger than the top. We get y equals 0. If I have 3x to the 4th plus x minus 2 over 5x to the 4th minus x squared plus 7, all the rest of that is very complicated, but the horizontal asymptote is actually not, because the biggest degree here is the same. I look at the ratio of those coefficients, 3/5. Okay, so these are actually horizontal asymptotes. And that's what we covered before, and you would have worked with that in 4.1. Now the question is, what happens if I have this? 2x squared plus x minus 3 over x plus 2. So that is a different situation than either of these. The numerator is larger than the denominator, and importantly, the numerator is 1 degree larger than the denominator. Numerator is plus 1, let me say degree of the numerator is plus 1, the denominator. It's 1 degree larger. And this is what's going to generate what's called an oblique asymptote. And oblique, just in math here for this situation, it means like an angle. You know, like your obliques are on your side of your abdominals, but in mathematics, it means kind of at an angle. So rather than a horizontal asymptote, an oblique asymptote is at some kind of angle. And let's see how this works and why this works. Turns out then, once the first thing and most important thing is to identify, right? So this is a great start to say, okay, I know this is going to give me an oblique asymptote because I've looked at the degree and it matches. So then the second step is say, okay, what is that oblique asymptote? Well, the way to find it is actually to rewrite this problem using long division, or synthetic division actually works too, if you're comfortable with that. But sometimes you'll have, 2x plus 3 or x squared minus 4 in the denominator. So you may need to use long division. So this has to be 2x here to give me the 2x squared. And then I also get plus 4x. I subtract both of those. I get minus 3x minus 3. So this is minus 3 here. Minus 3x minus 6. Subtract both of those, and I get 3. So what this tells me is that I can rewrite this problem as when I divide x plus 2 into this, I get 2x minus 3 as my answer, plus this remainder, which is 3 over x plus 2. So this is just like what we did in the last section. This is just straight long division. It's what we do with division. It's just rewriting the problem using division. Rewriting it this way, though, is going to allow me to see what happens to the function. As x goes to infinity, as x gets bigger and bigger and bigger, this part here goes to 0. I get a really large number on the bottom. 3 divided by a really large number is close to 0. So f of x then is going to get close to this line, 2x minus 3. Right? It's going to get closer and closer as x gets bigger and bigger, because this part is going to get more and more inconsequential, and so the whole thing is going to get closer and closer to this. And so this is actually my oblique asymptote. And normally we would write it as y equals 2x minus 3. This is my oblique asymptote. And graphically,
Dude, I do not know what the heck he does. I'm gonna have to just watch all of those later.
let's see here. There we go. So what this looks like graphically is, you know what this line looks like, y equals 2x minus 3. And, well, 2x would be a little steeper maybe, right? It looks like that. And that line is functioning like the horizontal asymptote does, right? A horizontal asymptote, you know, the function gets closer and closer to that. The same thing happens here. It's just rather than being horizontal, it's oblique. And now, you know, we'd have to look at some other features of the graph to know exactly what's going on here. I can see there's a vertical asymptote at minus 2. And, you know, I need to look at maybe the x-intercepts and y-intercepts and everything to be sure, but I'm pretty sure this function looks something like this. Still a function, but you see how it's getting closer and closer to this line as the x values get farther and farther out in both directions. Again, other things could be happening here. You know, it could be going up and down or have some other asymptotes. But eventually it's going to approach this line, y equals 2x minus 3.
So how did you just throw that oblique asymptote on the graph, like the 2x minus 3? Is it because when you solve for x, you get 3 over 2?
No, so it's just a line. So like I put this on the graph because when I look at this line, I say it has a y-intercept of minus 3 and a slope of 2. So I go down to minus 3 and I just go up 2 and over 1, and it's a pretty poor graph, but that's roughly what that looks like.
Okay, so will we always get an oblique asymptote that looks like that? Or what if we just get like y equals x?
Well, that's fine too. If y equals x, that's also a line. That line has a y-intercept of 0 because there's nothing there. And then it would have a slope of 1. So I just go up 1 over 1. Y equals x. So any time the degree is 1 larger, when you do the division, you will always get a line at y equals x, plus some other junk, right? But this other junk is always going to be larger on the bottom than the top. It's always going to go to 0. And to know that, you do know that, but it comes from really understanding how division works. So if you kind of understand when you're dividing, you're always going to get this situation. You don't need to really see that, but that's why that rule happens. If the degree is bigger, if this is like x cubed over x, then when you divide, you don't know what you might get. You'll get an x squared, and we don't consider that any kind of asymptote if it's not linear. Okay, but asymptotes can be horizontal or they can be on an angle. Also be aware that you get one or the other or neither. You can't have both. You can't have a line or a function that has a horizontal asymptote and an oblique asymptote. It has to be doing one or the other or neither. Okay, so the vocabulary there sometimes is confusing for students because it's like, well, is it a horizontal asymptote or is it an oblique asymptote? Well, they're kind of, end behavior would be like the umbrella term, like what's happening out on the ends. It could be horizontal or it could be oblique. But the good thing is the rule is always the same. You just do division, and you can ignore your remainder. So whatever you get here, this is going to be your oblique asymptote. It does often make the function a little bit harder to sketch because it's like on an angle, and then but it works. It works the same way as a horizontal asymptote in that I can decide kind of which part of that I am. Am I in the top or the bottom of it, or divides it up into sections, just like a horizontal asymptote does as well. Other questions? Did I answer that question? I don't always know. It's just one where it's nicer in class, right? Because I can see people sort of like nodding with confidence or like shaking their heads with disbelief, right? But here I'm flying blind a little bit. Any questions about those oblique asymptotes? Okay. It's again just straight long division, or synthetic division in this case, but in general, long division. Okay. All right. Well, that's kind of all I wanted to go over today. You should be starting your next section after today, right? So finish up what you need to today, and then our next section is a little bit longer in that rather than having 2 homework assignments, I think it's like 5 or 6 homework assignments. So as I state in the schedule, we don't have a take-home work due for this next section, so we'll wait on that. There isn't one posted for it, so I want you just to focus on the homework. That I think that's enough for this section. But I say this every week, but do get started on it early, right? I kind of recommended maybe even getting done with this early. It's hard to do, right, when the deadline I know I'm a person too, right? Deadlines are the way I get things done as well. So I understand, but what that means is you'll have a kind of relatively full 2 weeks here as you get through this next work. If you save it for like the end weekend, it's gonna be a problem for you. So please finish this and then move right into that next section so that you can hopefully ask some good questions when we come back and meet again next week, right? I think the questions today were very good. It shows you've been working and learning some things. So hope for more of that next week. Okay. If there's no other general questions, I will let you go. I know I have a couple people that maybe have some specific questions about things. So if you want to stick around, I can put you in breakout rooms so we can talk individually if you have some other questions, specific questions. Otherwise, have a good week and stay safe, and I'll see you next week.
You as well.
Thank
Thank you.
Yeah, take care. Be well.
Take care.
Thank you.
So like I do have a question about, so will the final be in Zoom or will we have to be in person?
Yeah, no, I think at this point it's going to be in Zoom. I just haven't gotten. I don't think it's realistic to say it's in person the way things are going at this point. So, so yes, we will plan on kind of the same setup that we've done before with Zoom.
Okay, that's all I really wanted to know. Thank you
Okay.
for that.
Yeah, of course. You're welcome.
I had some questions about like some past due homeworks and stuff.
Yeah. So I can just kind of speak generally here, and then we could go into a breakout room if you want to talk.
Yes, please.
More specifically.
Okay.
I do give credit for late work that's done. Not full credit, but it definitely does matter. So the take-home works are sometimes a little trickier because I post the key for those. So by the time those get made up, there's not as many points available for those. The web assigned homework and quizzes, you still usually I give you about 75% of the points back on those, especially if it's close to the due date. I often give even full points. So I can give you another day or two, like for the section 4 work. If it's older work than that, then usually there's a little bit of a penalty, but not enough to keep you from doing it, right? Because that's important. You can get through all of that, even if it takes you a little extra. I'm still willing, to give you most of the points for that, and it also will make a really big difference, of course, in your exam score, right? Actually working and doing the homework. So, so just for everybody who's there, if you have some late homework assignments, let me know about it, and I can change those due dates for you quite easily, and we can, then you just got to let me know when they're complete, and then I can go back and rescore those. If you have any missing take-home work, you can certainly just do that and hand it in. I see that when it's handed in, and so I'll go in and grade it, and I'll give you a little bit for that too, which is certainly better than a 0. Anything is better than a 0, and like I said, it will also help with your overall test score and kind of understanding the material. So with that said, I can, does anyone else have any sort of general questions? Otherwise I'll put you in breakout rooms, and I'll just slowly kind of work my way through everybody.
I think that's fine with me.
Yeah,
Okay.
same here.
Okay.